Okay, hello all. Today in this video we're going to be looking at how we can draw the first and second derivative of a given function. So here's our function that we have all sketched, and what we want to be able to do is draw what the derivative, so what the gradient is at a given point as another function. So what we need to do is we need to analyze what's happening in terms of the trend of the graph between all the points along the course of the graph. So if I just click in here, what we see first off with our f of x, this original function, is that it's decreasing and the rate of decrease is increasing, decreasing. So what you can see is that we've got a negative gradient here, and it's becoming slightly less negative as the gradient approaches a. And it's not doing this a uniform rate, it's changing the rate. So how is this going to translate into our f prime of x? Well, think about it. We've got a negative gradient, so I'll be looking in the negative section of the Cartesian plane, and it's becoming less negative as it progresses. So what we'd be looking at here is we'd be looking at having something where the gradient becomes less negative, because at point A here, where it translates, we know that obviously the tangent there of our f of x is going to be equal to 0, because look at it, it's a horizontal line, there's no slope, there's no change in y relative to a change in x. So there we go, we've sort of got a bit of a slope there happening, and as you can see, the rate of which the curve is a negative gradient is decreasing. It's becoming less negative, because look here, it's a much less than it is up here. It's less steep in terms of the rate of decrease. And of course, it's approaching the tangent of point A being 0. And that's why it will be 0 here, because it's on the x-intercept. And then we have our point of inflection up here, which shows us the next phase of what we need to do for the f prime of x. So in this case, we see that it's a positive gradient. You can see it's increasing as a positive gradient. So if that's the case, what we have is we have an increasing positive gradient, so it will be going up, like so, to point B, because it's becoming more and more positive. And then at point B, up here, we need to analyze what happens to our gradient to point C. So in terms of this, it's still positive, but as you can see, it's becoming less positive, because as it approaches C, again, the slope of the tangent line to C is going to be equal to 0 at that inflection point, because at the inflection points, the vertex is always, it's going to be 0 at the vertex, the gradient. So now, it's going to be positive, so it's still going to be in this part of the Cartesian plane, but it's going to be going down at a non-uniform rate, so a curve, until it reaches C. This is very rough, but I think you get the idea. Until it reaches C, again, where the gradient is going to be equal to 0, because, look, it's a flat line, no gradient there. So that's good. And now we just need to evaluate between C and D. Well, let's see, it's a negative gradient. And as it goes along, it becomes steeper. It becomes more and more negative. Because, look here, it's obviously reasonably negative there, but it's even more negative down here, if my paintbrush would work. Whoops. Oh, for some reason it must have changed colour to white. Anyway, what we'd do, don't like that, let's see, is there any way to change the colour up here? There we go, I think it's back again. Yep, okay, so it was double tapped. Anyway, it's becoming more negative until it gets to point D. And it's not uniformly becoming that, so that's going to be a bit of a slope. Sorry, I sort of messed this up. I know this isn't the best program in the world, and look, I've double tapped again, so. At point D, we have an inflection point, so that means that it changes direction. So what happens is our gradient is going to become less and less negative up to point E, where again, the gradient is going to be equal to 0. And then after that, we have something that starts off really positive and becomes even more positive. Look how steep that gets. So if that's the case, again, a non-uniform rate of change up to there, and it would just keep going. And there we'd have our derivative function, roughly, which would sort of more look like a parabola here. Let me just fix that up. Again, you'd be able to sketch it a lot better on paper than I could do using this program, but that would be our f prime of x, because it shows what's happening to the gradient at any given point across the function. What we'd do from that is we'd be able to draw the second derivative, which I'll let you have a think about, where we'd be able to evaluate what's happening to the gradient at each position across the f of x function. So we treat this as a function next time round, and then we say, okay, what's happening to the slope at any given point? So just remember, if this were to be, say, a line here, a linear rate of change, then our f prime of x would translate into being something horizontal, because it would be a constant uniform gradient change. But in this case, it's all mainly slopes, because the rate of change changes all the time. Anyway, there's the video. Hopefully you understood it and enjoyed it. Hopefully you're able to draw the f prime of x based on that. Again, just evaluate what's happening, positive or negative. Remember what happens at the vertexes. The gradient's equal to 0, and at inflection points it changes direction. And just say, okay, is it getting more negative or less negative, or what's happening? You just got to evaluate it and then draw it. It does take a bit of practice, but once you got it, it's pretty good, and you can draw the second derivative and maybe even the third derivative of this function. But anyway, hopefully that's been good. So see you later, everyone.